Hello everybody. Today we're going to go ahead and take a look at a very typical type of calorimeter problem. These can be rather complex because there's a lot of words in here. I would recommend a couple of things. One, organization of work. List the information. A lot of times students get the data mixed up between the metal and the water and the metal and the calorimeter. So you want to make sure you keep your data separated. And two, you want to make sure that you are, maybe draw some pictures, get a good visualization of what's happening. So I'll kind of show you how I solve these problems. Okay, first thing to do is read through the problem and kind of figure out what I'm looking for. And it says right here I'm looking for the specific heat of the metal. So I'm looking for the specific heat of my metal. So that's my goal of the problem. So it's the first thing I want to do is identify what is it that I'm looking for. All right, so now I'm going to go through, I'm going to read, and I'm going to pull out the information that's important. So I have a piece of metal, and I have a mass, so I'm going to list my information pertaining to the metal over here. I have a mass of the metal, which is equal to 37.7 grams, and it's heated to a temperature of 100 Celsius. Now, that's actually the initial temperature, so we're going to get it up to 100 degrees, because we haven't done the calorimeter problem. We haven't done calorimetry yet. Remember, calorimetry is when we take that metal and we put it into our calorimeter, which is going to have water in it, right? We'd have this cup here, and we're going to put the metal into the water. At that point, we are then doing calorimetry. So we're heating this off to the side. We're going to actually do this in a lab. You'll actually carry out this same experiment to determine the specific heat of a metal in one of the labs we're going to do. So when we do this, the metal is either going to absorb heat or lose heat. Well, I can tell that it starts at 100 and my temperature of the water is at 23, so it's pretty obvious that the water is going to gain the heat that the metal loses. Okay, so the metal is going to lose the heat to the water. All right, so let's continue pulling out the information. Again, I'm trying to think about what's going on. I'm listing my information. I'm identifying my unknown. So I'm going to put here some information pertaining to the water. Because of calorimetry, the general idea is that we're using this equation. Q of the system is equal to the Q of the water. This is the first law of thermodynamics, which is basically focusing just on the water. So we're saying that the surroundings is just the water. So we're not really looking at the entire surroundings, just the water. And that's what the assumption we make when we are using calorimetry, that all of the heat from the metal in this particular problem is going to go into the water. Now we just have to put a little sign notation here to show that the sign is opposite of whatever the water is. Because remember, if it's exothermic for the metal, it's endothermic for the water. So we've got to keep the sign notations clear as we're doing this. So this is the general equation or premise that we use when we are dealing with calorimetry. Alright, so let's go back to pulling out the information. So the initial temperature of the water, okay, is equal to 23.1 grams. Now my initial mass, which I kind of stepped over, is 75 grams of water. Okay, so 75 grams of water. Okay, after the metal is added, so we add the metal, the temperature of the water and will increase until its temperature and the temperature of the metal are the same. So the temperature of the water, as we know, whoops, not a 2, but let's put an F here for final, is going to get to 30 degrees 0.6 Celsius. Okay, so 30.6, so the temperature of the water is going up, and the temperature of the metal is going to get to that same final temperature. It's going to keep transferring heat until they come to thermal equilibrium, or their temperatures are the same. So it's going to keep transferring heat until they're both the same temperature, and then we don't see a transfer of heat anymore. So these two things are the same at the end of the experiment. Okay, well, we know the specific heat of water, okay, is equal to 4.184 joule gram degrees Celsius. We're looking for the specific heat of the metal. Okay, now we need to find, in order to find specific heat of the metal, we need to know the heat that the metal, released, because we know it's releasing heat, and we need to know the mass of the metal and the change in temperature of the metal. Because we know these three things, we can then solve for the specific heat. Well, good, I know the mass of the metal. It's given right here. I could find the change in temperature. Remember, changes in temperature are always going to be final minus initial. So let's put it over here. Change in temperature is always your final temperature minus your initial temperature. Okay. Now, I can't find this one. So I got the change in temperature. I could find that, but I don't have this, right? I don't have the heat that the metal lost. So what I'm going to do is I'm going to use water for that. Water, I can use this information. I could say I know the mass of the water, I know the specific heat of water, and I know the change in temperature of the water. So I can figure out all of those, and I can find out how much heat that the water absorbed. Okay, so my change in temperature for the water is going to be the final, which is 30.6 minus 23.1 degrees Celsius. I just noticed that I put a gram here. I meant to say Celsius. So my change in temperature, when I do that subtraction, comes out to be a positive 7.5 degrees Celsius. And that makes sense because the temperature of the water is going up. So I should see a positive increase in this. Why? Because this is endothermic, it's being added. It's very important to keep in mind that the change in temperature is going to tell you whether heat is being released or absorbed. So it's a good idea to keep that in check as you're going through the problem to make sure you're on the right track. So 75 grams. My specific heat is 4.184 joule gram degrees Celsius. I'm going to plug in my change in temperature, which is 7.5 Celsius. Celsius temperature cancels, grams cancels, I have a unit of joule. So the water absorbs 2,353.50 joules of energy. This is the amount of heat that the water absorbs. Right? It's absorbing this amount of heat. Where's all that heat coming from? It's coming from the metal. So what we have to do is we have to use this equation. Q for the metal, which is our system, is the same as the water, but just opposite in sign notation. So before I can plug it into this equation, I have to make this energy negative. All right, so I'm going to solve for this on the next slide here. So my specific heat is going to be equal to Q for the metal over mass of the metal and the change in temperature of the metal. Now, as I said, I have to do a negative 2,353.50 joules over my mass of the metal, which is 37.7 grams. And then when I calculate my change in temperature for the metal is going to be 30.6 minus 100 Celsius. So when I calculate the change in temperature here, we see that the change in temperature is negative, and it's a negative 69.4 degrees Celsius. Really important to keep that in mind because negative 69.4 tells me that the temperature is going down. Right? Temperature is going down. Well, if the temperature is going down, then Q has to be is going to be negative, right? So negative for Q. So these two will cancel out. Specific heats are never negative. The masses are never negative. These two, the heat and the change in temperature, go hand in hand. If this is negative, then your heat is negative, and then they'll cancel each other out every time. So my specific heat when I'm finished, and I do this calculation, comes out to 0.8995, and if I round to the correct number of significant figures, 0.900 joules gram degree Celsius. I keep all three of those units in here, and that is my unit for specific heat, and that would be the specific heat of my metal. All right, metals tend to have a low specific heat because they don't take a lot of energy in order to change a temperature 1 degree Celsius. Anyway, one last thing I want to leave you with before we end here is take a look at the change in temperature here. Change in temperature for the metal is almost 70 degrees Celsius. Okay, and if we go back and look at the change in temperature for the water, change in temperature for the water is only 7.5 degrees Celsius. Remember before I was telling you temperature does not measure heat, because look, there's a change in temperature is only small for the water, while the change in temperature for the metal was really large, but they transferred the same amount of heat. The same amount of heat went from the metal to the water, so if temperature were really truly measuring heat, those two numbers should be the same. The reason they're not is because the masses are different and the material is different, right? The fact that it's metal versus water has a different ability, and the masses are different. So those two things combine together to give you a different change in temperature. So temperature is a measure of average kinetic energy, and it only indicates whether the heat is being added or released. Okay? So we don't say we add temperature, we say we add heat, which causes temperature to go up. All right, guys, thanks a lot. I'll talk to you later.